We want to take a look now at solving initial value problems and boundary value problems. They're different. If you have a differential equation and you're given initial conditions like this, let's suppose that you're looking for a solution where y of 0 equals 3 and y prime of 0 equals, let's say, 4. That's an initial value problem because you're putting in the same values, the same inputs. Now, if you have something like this, so this is the initial value problem. A boundary value problem would look like this. Y of 0 equals 3 and y of 2 equals 7, something like that. And the difference is you're putting in different values. And usually those values that you're putting in are boundary values. So maybe you're talking about this solution on this interval from 0 to 2. Okay, so that's what we're going to look at. Now, first of all, I want to point out something to you. A lot of times you'll find yourself with something like this. Let's suppose we've got y prime equals, let's say e to the x squared, something like that. And let's suppose that we've got some initial condition. We say, okay, y of 0 is equal to 0, let's say, something like that. You would have a hard time solving this, but what you could do is you could say, well, I'm going to say y is equal to the integral of e to the t squared dt. See, just put in a different variable in there and go 0 to x, like that. And then what you have is you have your solution. I mean, you've not been able to integrate that actually, but there is the solution right there. And notice the derivative of that. If you take the derivative, d dx, you get, d dx of that interval. If you do that, you get e to the x squared. And that's what you were supposed to get. In other words, the derivative is that. So now, if you had something like this, let's suppose you had y prime equals e to the x squared, and you had this initial condition. Let's suppose you had 4, y of 4 equals 0. Then you could write that as y equals the integral from 4 to x and e to the t squared. Now, you may be wondering, well, why? Why would that work? Well, because if you've got this, if you've got y of 0, or you've got y of x. This is a function of x here, and you're going from 4 to x, e to the t squared dt. Now, what you're trying to do is you want to say, okay, when I find my solution, when I put in a 4, I want to get a 0 out. Let's see if that works. Y of 4 equals, putting in a 4 for x. Look. That right there is 0. When you integrate from a number to itself, you get the integral to be 0. So that is 0. Now let's suppose that you had something else. Let's suppose that you had this thing. And they said, okay, y of 2 is equal to 5. Something like that. Well, you could write your solution this way. You could go from 2 to x, e to the t squared dt plus 5. You could do that. I mean, that would work. But anyway, that is, sometimes we'll write the solution this way instead of trying to integrate it. And sometimes we get something that we can't even integrate. But this is one of the ways we can write the solution. Now, what we're going to look at today is Green's functions. And we're going to derive the formula for Green's functions from variation of parameters. We've done, we've worked with that before. But let's suppose we've got a differential equation like this one right here. Okay, we've got this differential equation. And let's suppose that y1 and y2 form a fundamental solution set. So they're independent. And let's suppose further that we have these initial conditions. Now, I'll bring that into, I'll bring that up later, but let's just suppose we have that. Now, we learned that we can find a particular solution this way, okay? We use variation of parameters, and we start off with u1, y1 plus u2, y2. And we set up these determinants, okay? We had u1 prime equals this, u2 prime equals this, and by the way, this is w of x, this is w. So they're both the same. But anyway, when we work through this, notice you get this minus this is what we get. And on the bottom, this product minus this product, we get this. Okay, that's that Ronskin down there. Now we do that for u1 and we do that for u2. And what we want to do is we want to integrate. So in other words, I need to find u1. And when I find u1, I'm going to multiply that by this integral. See? Or not that integral, but this solution. So I'm going to find u1, and I'm going to get u1. I find it by integration, and then I multiply that by y1, one of the known solutions. Okay. So here we go. I have y1 times the integral of this thing. See, there it is. And notice I'm not integrating it. I'm just starting at some value here, x naught. See, x naught right there. And I'm going up to x. But there's what I'm integrating, right there. Okay. And I just changed the values of the x's to t's. Now, for y2, for the second one, I've got y2 here, and I'm integrating this. So there's y1t, f of t, over w of t. Okay. So I'm just integrating that. Now, notice that these have the same bounds of integration. So I'm going to combine them into one integral. And what I get is this. Right here. I get this integral. And notice I've got the f of t out here. Okay. And what I have now is an integral that looks like this. I've got this thing right here, which I'm designated that as capital G of x comma t. And then I've got this thing over here, f of t, which is what's on the other side here. Okay, the function. Now, this thing right here, this part right here, we call that the Green's function. And notice how it works. You've got y1 of t, y2 of x, minus y1 of x, y2 of t. So you see you start off with y1t, and then over here y2t, and then whichever has the t, the other solution has the x. So y1t, y2x, minus y2t, y1x. And it's all over this w. Okay, so we're going to use this to solve differential equations. So let's suppose that we have this differential equation right here. Okay. Now what I want to do, first of all, I want to find the homogeneous solution to the associated homogeneous differential equation. So we know how to do that. I assume the solution is e to the mx, and I go through that process, and I get my auxiliary equation here. Factor it, and I solve it and find that on the one hand, m equals 1, which gives me e to the x. On the other hand, m equals 3, which gives me e to the 3x. And then I plug it into this Wronskian, and I get 2e to the 4x. Okay, so we keep that in mind. Now, that's the first step. Okay. Now, here's what I do now. I'm going to actually find the particular solution. And I'm just going to plug it into my formula. Now remember, we have the Green's function, which I should put that in green here. This one. Okay. So I'm going to put that in, and notice what I have. I have y1 of t. So here it is, y1 of t. There's y2 of x. Minus y2 of t, y1 of x. All over this 2e to the 4t. Now that 2e to the 4t, we got that earlier. Right here. Okay, so there we have it. And then I put the what's on the other side, x squared, I put that right here. So notice there's the Green's function. There's the t squared. It was x squared. And I'm going from 0 to x. Okay? And I'm integrating with respect to t. Now, if you look at that, we could work through this a little bit, and this is the particular solution here. This right here. Now, notice that this is a generalization of the variation of parameters. You could get this same result with variation of parameters, and I went ahead and integrated this out. You know, I separated it and went through and integrated it. You don't have to do that. Okay? You won't be able to do that every time. But anyway, there's my work, and I'll upload these notes for you. Now, one other thing that I've done is I've also went through and worked this just with variation of parameters. And I got the same result. But anyway, I'm not going to take up time talking about it. It's in the notes, and you can look it over. Now, so let's look at a couple of equations here. Now, one of the good things about Green's function is Green's function doesn't have anything to do with what's over here. You know, you've got your equation on the left-hand side, and then you've got your whatever on the right-hand side. Now, notice these two differential equations right here are the same except for what's on the other side. See, you got y double prime minus y. So if they got the same auxiliary equation. So I find two solutions. I find y1 equals e to the negative x and y2 equals e to the x. And then I go through this process, g of xt, finding my Green's function. Okay, and get this right here over this w, and I get this. Yeah. Now, so that's the preliminary work, and you might wonder, well, how'd you get from this to this? Well, remember, hyperbolic sine, let's just recall, hyperbolic sine of x is equal to e to the x minus e to the negative x over 2. So I had that same situation here. Instead of x, though, I had x minus t minus e to the negative x minus t. So it's the same thing, and the hyperbolic function was just cool. So, it's just something, it's not that important. The important thing is that you get this, okay? Or that that. Now, if you're going to, so now we're ready to write the particular solution. First of all, for the blue, notice I've got this, and I put 1 over t, see, for this one, 1 over t. For the other one, Looks very similar, except I've got e to the t because this, that's e to the t. That should be e to the 2t. There we go, e to the 2t. And I notice I made that mistake throughout. So I won't pay any attention to what I've got here. So on this first one, on the blue, you'll notice I gave you initial condition. I said, suppose y1 is equal to 0 and y prime of 1 is equal to 0. And notice how I wrote the integral right here. Okay. So y1 is equal to 0. Y prime of 1 is also equal to 0. And you can check that out. Notice that y prime is going to be equal to, when you differentiate this integral right here and plug in an x for t, you get hyperbolic sine of 0, which is 0. So it works. And now this one over here, I won't go ahead and work through this because there's 2. There we go. Okay, now I want to look at another one real quick here. And like I say, I worked these out in detail. I'll just kind of walk you through it. But notice that I've got this differential equation. I've got initial conditions here. This is an initial value problem. Okay, notice they start at the same place. I set up my auxiliary equation and I find that m equals plus or minus 2i. And we know that we can write the solution this way. Okay. Now, what we're going to do is we're going to say, okay, for y of 0 equals 1, let's just put in a 0, and when we do that, we find that C1 equals 1. Okay? So C1 equals 1. And then we say, okay, well, let's try y prime, and we take the derivative, and then we plug in a 0, and we got negative 2. So for that one, we get this. And what we find there is C2 equals negative 1. So now we have this homogeneous situation here where C1 is 1 and C2 is negative 1. So we have this. Okay. Now, what I want to do, we know from this that y1, we've got a solution, cosine 2x. That's a solution for the homogeneous equation. So is sine of 2x. That's a solution for the homogeneous equation. Now, so I've got 2 solutions here. And what I want to do is I want to try to find a particular solution. Okay, so I go down here and I've got, notice I've got y1, its derivative right there. I've got y2 and its derivative right there. And I go through the process here, the determinant, and I get 2. And then I plug into the Green's function. See? Plug in into the Green's function. And I get this thing. Now, you might be wondering, well, how did you get from here to here? Now, here, I was just plugging into the function. But then I made this leap. Well, recall, back in your younger days in trig, you had this identity. Okay. Sine of alpha minus beta equals sine alpha cosine beta minus cosine alpha sine beta. And using that identity, we don't have alpha and beta. We have 2x and 2t. So here's what we get. Okay. So that means that I can write that Green's function this way. Okay. And then we've got what's on the other side, sine 2x. So there's 2t there. and our initial condition is 0. You plug in a 0, you get out a 0. So this is our particular solution here. Now, as far as our just the general solution, we've got cosine 2x minus sine 2x. Now, it looks like I miswrote something here. So this is cosine 2x minus sine 2x plus the particular solution. So that's the complete solution there. And that's how we deal with these initial value problems. Now, let's go down here and look at boundary value problems. Now, boundary value problems are different because generally we're plugging in values. Okay, so initial value problems, usually we're plugging in the values at the very beginning of our interval. Not here, not for the boundary values. Usually we're plugging in values, like in this case, we're plugging in values from 1 to 2. Okay, so we're looking at the solution from 1 to 2, the boundary values. The thing to remember is that these values are different. I've got 1 and 2 here. Now, so I want to solve this equation. Now, you might recognize this as one of those Cauchy-Euler equations. And we assume that the homogeneous equation has a solution of y1 equals x to the m1, y2 equals x to the m2. In other words, it's x to some power. So we put in, we plug in, we get the auxiliary equation, and we get m minus 3, m minus 1 equals 0. We get this, okay, this right here, okay? And then when we factor that, we get this. So now we get y of x equals c1x plus c2x cubed. Okay. Now, we've got two problems that we're going to solve here. First of all, we're going to deal with the homogeneous situation. We're going to use these boundary values up here and find a C1 and a C2. That's what we're going to do first. So, notice, if I put in a 1, I get C1 plus C2 equals 0. Now, these are just constants, and I notice that C1 equals negative C2. Now, I can let C2 be anything I want. I'm going to let C2 be negative 1. Okay. Now, if C2 is negative 1, C1 is 1. So that means that my solution, my y1, this is what we're going to call y1 here. I mean, it's confusing because I was talking about y1 up here. This is like my new y1, okay? So I've got x minus x cubed. Because C2 is negative 1. That is my y1. Okay? Now I do the same thing. I put in a 2, and I get 2c. See, I'm just putting in a 2 here now. I get 2c1 plus 8c2 equals 0. And I get c1 equals negative 4c2. C2 is negative 1, so C1 is going to be 4. Okay? So I've got now 4x, put it in place of C1, and then C2 is negative 1. So this is y2. This is my second solution. So this is the new thing we're doing here. We've got two solutions to deal with this boundary value problem. Now, the next thing I'm going to do is I find the Wronskian, right? I put in y1, its derivative, y2, and its derivative, and I find the value to be, the w to be 6x cubed, okay? That's what's going to go in my denominator. Okay. Now, here's what we're going to do with these boundary values. Notice we've got this interval from 1 to 2. We're going to go from 1 to x, and then from x to 2. Okay? So dig how we're going to do this. We're going to have 2 of these green functions. Now, I'm going to take the y1 first. I'm going to take the y1 evaluated at t. So I take the y1 evaluated at t times the y2x over w. Okay. In other words, I take the part associated with my y1. Okay. In other words, the y1t. Now that's going to be for the integral from 1 to x. Here, from 1 to x. So notice, there's y1t, y2x over 6x cubed. Now, for the rest of it, in other words, this is from 1 to x. From x to 2, I go y2t, y1x. Same process. So you see I've got it here. Now, before I go any further, what I've got to do, remember, I've got to plug in. I divide out the x squared here. Okay. So I divided out the x squared, and I get this. I've got to put this at the end of my integral. So I put a 24t cubed in here. But it cancels out with the t cubed on the bottom. So see, I put in a 24t cubed here, and they both cancel out with the t cubed on the bottom, and I just pull out the 24. Yeah. Now, that is my particular solution right there. So this will give me the particular solution that satisfies that boundary value.